Okay, here we go. I used to do a little competition between students, 4 students, to see who could empty their container quickest, but then I didn't get through the actual math, and then people weren't able to do the homework. So imagine 4 students, one of which had just a regular sized container filled with water and a normal straw, right? Then the next person had to do a straw that was basically from almost the ceiling all the way down to the ground, but the same size container. And then another person, I don't know why I put mustard. It was a milkshake. It was a milkshake of fluid, really thick milkshake that, I mean, he was almost passed out trying to do that. Okay, and then the last person, I did Tupperwares, and so this Tupperware had the same face here, but it was much longer, and that person had to empty their container, although it had the same height, right? So, between all 3 or 4 of those pictures are meant to communicate the big idea of the day. The big idea of the day is how much work it takes to empty a container by pumping fluid out of the top edge, all right? All right, now consider those variables here. The things that seem to relate to work or impact the amount of work that it takes are what? Distance, the straw length, the distance you have to pump the fluid, yeah. Having to pump a layer way high is more work than it takes to pump a fluid number.
Density.
Density, yes.
And force.
And
Amount.
volume, yeah. The volume. All right. Now, in terms of math relationships to work, is it the more distance, the more work, or the more distance, the less work?
More distance, more work.
More distance, more work. That's directly proportional, yes. What about density? Direct or inverse proportion? Direct. The more dense, the more work. And what about volume? The more volume, the more work.
More, yeah.
Yeah, so it's 3 direct. So then that means that work depends on distance, density, and volume. Okay, got that big idea. Why calculus?
Because the volume is you see
No,
how much
it feels like the volume of each of these slices is the same.
you could find the change in work over a period of time.
Just think distance. How far this slice needs to be moved versus this slice? Do they need to be moved the same distance to get to the top?
Oh,
No. So they all have different distances. Each slice of volume is a different distance from the top. And that's why it requires calculus. If each one varies, if each calculation varies vertically, then what is going to be the variable of integration?
dy.
Yeah, we'll have to use y and dy. Alright? Alright, let's get into some examples here then. Alright, so say you drew a rectangular prism of 8 centimeters by 6 centimeters and a height of 10 centimeters. Something like that. It says it's half filled with water. So the total height is 10. The actual amount of fluid is 5 centimeters. You with me? All right. And we're going to put a pump at the top and pump it over the top edge. I am aware it's easier to put a hole in the bottom of the container, but that ruins the container. So we're going to, these questions are how much work required to pump fluid out. It doesn't always mean fluid, actually. We'll talk about that later. But that's the idea. Now, first, let's talk about units. If water is 9,800 newtons per cubic meter, we probably want to convert all to
Centimeters or meters.
meters, all right? let's do that. 8 centimeters now is gonna become,
0.08 meters.
and 6 centimeters,
0.06.
and 10 centimeters.
0.10 meters.
Okay, cool. Now, the origin. Where should we locate the origin of our container? We try and get it into the first quadrant. It's just easier than
Bottom
if
left.
bottom left, right? So let's put the bottom left there, and this will be 0.08, and this will be the 0.05 and 0.1 kind of stuff. And then if you want to draw the other dimension, that's fine. It depends on you. You with me? Okay. All right. Would you start then, please, by writing the big idea, the formula? Work is rho, distance, and volume. And it's infinitely many calculations because each little slice has its own distance to get pumped. So I need to make infinitely many calculations of sheets that are paper thin being pumped out of the top. All right. Finding the components. Plug it in. Plug in. Rho. It's water, so 9,800. I'll do units at the end, so leave a little space underneath this. The distance. So imagine there's a slice here at 0.02. I think you'll agree there's some slice at 0.02. If I'm pumping it to the top of the container and out, then how far would it have to be pumped? 0.08, yeah? Now, that's because, I assume you'll say that that's because this distance is 0.1, this distance is 0.02, so this distance then is the difference between the two. Total minus part is 0.1 minus 0.02. Now, generally speaking, if this is a y, then it's 0.1 is total, y is this part, so the distance is 0.1 minus y. You know? All right. Volume is a reference not to the volume of the whole container, but just what's the volume of this paper thin sheet of water. So, I think we can see that the volume of this is just a rectangular prism. What's the length? 0.08. And the width?
0.06.
And the height? dy. Yes, okay. So 0.08, 0.06, and dy. And what are the bounds? We have basically two choices, 0.1 or 0.05. 0.05, because I'm only pumping where the fluid is. And so if you throw that in your calculator, you may use your calculator today. We'll focus not on the integration technique, which you have. Yes? Good question. Because when I have this slice here at 0.01, I don't want to get it to the surface of the fluid and drop it. Then it's not out of the container. I need to get it all the way to the top edge of the container and out. And so, for force, it would be the surface of the fluid, yes. And I will do a compare and contrast on the back of these things. Okay, so what'd you get for the answer? Okay. I've calculated. I'm sorry, 0.1764. Okay, units. Okay, so let's talk the units. The units on the weight density are newtons per cubic meter. What are the units on distance? What are the units on width? And length? Does dy have units? It does. Meters. Meters cubed cancels out 3 of the units. You are Newton meters, and Newton meters are
Joules.
joules.
Hey, except for the physics stuff.
Yes, Heather. This guy? Good question. So I will get to this on the notes on the back of this, but the hardest part of this is there's so much overlap to force that people get the two confused. Now in terms, it goes to what you're trying to do. I'm trying to take this sheet, let's say I look at the slice at 0.01. I don't want to get it to the top of the fluid and drop it, because then I didn't pump the fluid out. I need to get that slice all the way to the top of the container and out. So I have to take it all the way to that top edge of the container. It's not relative to the fluid itself. It's relative to where do I have to get it to. So that's the distinction. And I will talk about that more in a second. Okay? All right. Let's try another here. Always, if it's a circle, put the origin at the center. Okay, so I know that work is rho, distance, volume. Writing a formula in math is just good math. It communicates to the person, this is what I did. In case there are multiple formulas used or people weren't sure what you're doing. It also helps you remember it quicker if you write it every time. Now we're going to draw or locate our origin. We're going to put it at the center of the circle. Okay, so let's label the picture here. What are the right and left edges? -4. Like, what about the bottom edge? -4, right? Now let's get into whether it's filled or not and what level it goes to. It says it's filled to a height of 2 meters. So that, if I start there and I go up 2 from there, what's the Y value of the top of the fluid? -2, yeah? With me? Okay, because it has a height of 2, it's going to go up from -4 up to units to -2. All right, cool. Now let's talk components. Rho is a constant, and in this case it's 8,000. You can put it up front of the integral. So the distance. Okay, so how far am I going to get? Do I need to pump a slice to 0.2 or to the 0? To the 0 to get it to the top of the container. So what's the distance if this is 0.4 and this is y? Actually, never mind. Just let's just keep it universal. What's upper minus lower to get a positive value? 0 minus. Okay, cool. All right, for the volume of this, this again is volume. It's not the volume of a cylinder. It's the volume of each of these little sheets. So we're really sectioning this into lots of little slices, paper-thin slices of water, yeah? But they're all rectangular in nature. So when I say volume, you should think many times with Earth's height. The length, how long is this thing? 12. All right, now let's talk about the width here. The width of each of these slices. Constant or varying? X or 2x? 2x. And the height of each slice? dy. All right. So 12 is fine, 2 is fine. X can't stand, though, if I'm integrating with respect to y. So what's the relationship between x and y? X squared plus y squared equals 16. Therefore, x can be replaced with root 16 minus y squared. All right, I have my volume pretty much nailed off to the side. You want to kind of compartmentalize the problem, take little bits and pieces to keep it from getting unmanageable. So I'm going to bring back my volume, 12 for the length, 2 for the symmetry component to the width, and 16 minus y squared square rooted for the varying component of width, and dy for the height of the sheet. All right, limits of integration. -4 to 0.
-4 to -2.
Which one?
-4 to -4 to -2.
It is -4 to -2. I only need to pump what the fluid is. And so throw that into your units, or your calculator, excuse me, don't forget units. 12 and 2, obviously you could put them out front. Really, you're just sponging off everybody else? What else?
No, I have a question.
Hit me.
So, why is it -4 to -2, but it's 0 minus 1?
Good question. These are reflecting different things. These are talking about the places, the Y values where I'm pumping sheets of water out. And the water are from -4 to -2. That's why they're. This is the distance I'm taking those sheets. And those distance, they're not relative just to the surface. They're going all the way to the top of the container. And so that's why that's using 0 rather than -2. They really are different things. This reflects where the water is. This reflects the distance at the pump. And the distance has to be to the top of the container, not the fluid.
So, like, basically the integral is initial.
Yes, you could say that. Okay, so we have an answer?
266.
Well, you can't.
2,000,000.
2,430.
Did you say 660,000?
Yeah,
Okay,
430 and 4/10. 400s.
which one?
Hundreds.
400s. Joules, yeah? Okay, do we all agree? All right, now let's pause and do a little compare and contrast because the biggest problem by far is that people get the two components mixed. So, when we do force, first of all, the calculation is rho depth area. And I would encourage you to not just use generic D because D could be distance or depth. And so you need to communicate that force is based on how much depth. The more deep a slice is, the more pressure there is, and the more force there is, right? Now, on the limits of integration, the bounds for the integral go from fluid low to fluid high. I'm only calculating the force that the fluid itself exerts on the face, not any airspace up at the top, yeah? So you should only be focusing on the fluid here. Depth, remember that depth doesn't relate to how top of the, I don't care if the top of the container is 1 billion meters tall or 2 meters tall. Depth matters not one bit to the container. It matters where's the surface of the fluid, right? So depth is the fluid surface minus water. And the area is just the area of a slice, which is typically a rectangular slice, and it's either constant or x or 2x wide and dy high, right? Now if you compare that to work is rho distance volume, not area. How wide a container is, I don't care how far a container goes back for a force, because the force is going to be the same on the face. But for volume, it does matter how far it goes back, because you'll get more volume now. So in this case, the limits of integration, it's still the work to pump out the fluid. So the bounds are still, where is the fluid? Fluid low to fluid high. That's nice. That means that when you integrate, the bounds are always fluid. Always. The distance, however, is going to be different because you're not trying to take slices to the surface of the fluid and drop it. That doesn't remove the slice. You need to take it to the top of the container and drop it. So the distance is top of the container minus what? And the volume then will be the volume of each slice. it'll often piggyback off the area and just have the length dimension added in. Alright, so the big differences, really the only two differences are the distance and the volume being different than depth and area. The bounds will be the same, the row is the same. Alright? Okay, so let's look at a case. So trough, triangular face, top edge 3, side 4. Distance between the bases 7, filled half the way up with gas. I got it. Find the force the gas exerts on the face. Let's set up the same origins so we all have the same setup, all right? First, where do you want to put the origin?
Top right.
Top right.
Wait, yeah.
Okay, strive to put it in the first quadrant.
Okay, so no.
Wait, that's hard.
So, is there any reason that I can't draw this that way?
No, you can.
You can absolutely do that. Do that. Okay, you're not breaking that. The force is the same whether it's this way or that way. Same thing. Okay. Now put the origin at the bottom.
So there was no right answer.
Yeah, I was hoping to think outside the trough, but whatever. All right. Now let's get our picture. Top edge is 3, side edge is 4, halfway up. So actually, I put 4 here, 2 there. Halfway up is important. And whether you draw the 7 here or you doctor up your picture here, that's up to you. Some people are artistic and like to look cool, and like it to look cool, not themselves to look cool. And like that, yeah? Okay, now, let's start with the thesis, the formula. What is the plan for force? Rho dA, rho depth, area, cool. Rho. Actually, why don't you do force? You've been doing force forever. You can do force. Oh, jeez, I gotta do something for myself.
So the height's 4 in this? We've been doing force for a while. No, we've been doing it for.
The height of the slices?
Just like a yeah.
Do what?
Hey.
So we're 3 forces. Pi. 3. Ooh, there's pi. There's no pi. That's for 3. Oh my god, I got the.
It's not the third time, guys. There's no way. There's no way.
I got it. There's no way. How? Oh my goodness. How? What is this? So that problem is what? Let's find out.
Are you ready?
I got a strange. I got a long.
Okay, bounds. 0 to 2. Depth, do I use 4 minus y or 2 minus y? 2 minus y. Use your notes right there. Fluid surface minus y. Okay, the area of each slice. These are little rectangles, yay? What's the base of each rectangle? Constant varying x or 2x? A single x. And the height?
dy.
dy. What's the x relationship to y that we can use to substitute in? Let's see, why did it help us then to put the origin where we did? Yeah, the y-intercept of the line is 0, so there's no y-intercept. The line's a lot cleaner. It's just y equals 4/3 x instead of up here or something where I gotta have a y-intercept. So x is then
3/4 y.
So x is 3/4 y. So we're gonna integrate Q minus y for the depth, and the area is 3 force y dy. If you set it up that way, tell me what you got for next.
600. The integral is just one.
That's it?
Yeah.
Newtons. That integral came out to be 1. That's crazy. All right. Let's go then to the work. If I pump out the fluid from a hole in the top of the container, how much work will it take? Rho distance volume is the idea of the day. Rho is 6,600. The bounds, 0 to 2 or 0 to 4?
0 to 2.
0 to 2, it's still where the fluid is. The distance, 2 minus y, 4 minus y.
4 minus 4 minus
4 minus y, we have to take it to the top of the container now. The volume, how will it be like the area, how will it be different?
7.
And it's length times width times height, so I'm going to take that width and height of dy and just keep it and multiply by a factor of 7. You with me? You don't have to reinvent the wheel on the width and height of the slices. All right, throw that into the calculator
Bad boy.
and throw some joules on it.
Look.
Slap. And then what do you get?
184,800.
184,800 joules. Questions? Ladies over there, how we doing? Senior ladies?
Wait, you guys want
Yeah, you, Bailey. How you doing? Okay, you're trying. That's good. Senior ladies, you want to make a bit? This line here goes up 4 over 3, and that's how the equation, but we need to solve that for x, so that's where 3/4. So it's the equation of that line solved for x. Okay? And I appreciate that you don't just let stuff go. You ask questions. That's good thinking. All right. This one's a little crazier. A barrel with radius 0.4 meters, height of 1 meter, filled. Okay. Force against the side of the barrel. The barrel's lying with the circular face down. So it looks like this. And it has a radius of 0.4, a height of 1. And we're going to talk the force on the curvy face and work required to pump out the fluid. All right, so circle, put the origin at the center. The question is top or bottom? Let's do the bottom, so at least we're dealing with positive. All right, so we're going to put the origin there. Cool. A, force, formulaically is rho dA. D standing for depth. And the area is the area of a slice, not the area of a circle or something crazy, right? The rho, if it's water, rho is 9,800. What are the bounds if it's filled?
0 to 1.
0 to 1. What's the depth of each slice?
4 minus y.
What's the... Okay, so the area of each slice, now I'm talking it's exerting force against the side, so I need to say how much area to that line that feels force. Yeah, so let's go, remember that this area of this line is an unwrapped rectangle where the base is 2 pi r, and the height is dy. So the area of each slice is 2 pi. Is r varying or constant? Constantly 0.4 dy. Throw that into your calculator. Oops, that's Newton's, not joules.
told me. Oh my gosh.
What'd you get?
12,115. No, it's 12. What not? Oh, I did something wrong there. Oh, I did .04, not point.
0.4.
I did point.
Okay, do we agree with 12,000-ish newtons?
Now we do.
Okay. Let's talk work. Rho distance volume of each slice. Rho is 9,800. Bounds.
Still from 0 to 1.
Still 0 to 1. Distance.
Still 1 minus y.
1 minus y. When will those are coming out the same? Is that always the case?
No.
When will that be? When it's filled, the top of the surface and the top of the container are the same. All right. Volume.
Would it be just the volume of a circle?
The volume of a circle is two-dimensional, so no, good try. But volume of a cylinder, yeah. What's the volume of a cylinder? Pi r squared dy. Okay. Pi r squared dy is r constant or variable? Constant. And so 1 minus y pi and 0.4 squared dy. I imagine that 0.4 will cause it to be a little smaller answer. 0.4 squared is the even squared, 0.16.
It's just calculus.
That's all it is. Yes, sir. 2,468. 63. 008 or 9.
Oh, no. I told you that.
Whatever, 8 or 9. Okay. Be down. Okay. Let's try one on the homework. This is not easy, but then he throws one of the hardest ones to you the first day. So I'm going to walk through 4 on the homework.
Oh,
Okay. So he says it's filled with water. I think. Actually, I don't know that.
Does that mean the bottom is 6?
No, it's not water. It's 6,000. And the depth is 2. Oh, that's fine. It says it's 15 meters long. That's fine. The hard part is the face. The face is an isosceles right triangle. So he throws some geometry at you with an edge of 5. So,
It's a triple, right?
we'll get to that. So let's put the origin at the bottom, shall we?
Yes.
All right. If it's isosceles right, then this is the right angle. They tell you that these are 5, and if it's isosceles, that must be 5. And they also tell you it's filled to a depth of 2. 2. Okay, are you with me so far?
Yep.
All right, and it's a work problem. So, get started, and we'll talk it over once you run into an obstacle.
Great. I already forgot. Oh, wait a minute. 0 to 2. How much in full? Full. No, it's the fluid boat. Fluid boat. And then it's oh my goodness, you were. Oh, you're talking about the bounds. I got it. Oh,
So the bounds are 0 to 2, and now we're to the problem of where's the top of the container, right? It's not a 3, 4, 5.
Oh, wait, is it just flat?
It's isosceles. Yeah, so it is a 45, 45, 90. Now, this is 45 degrees, and this is 45 degrees, but when we split it, Is that a new 45, 45 negative? It is. So this is 45. So the question is, if I gave you a geometry problem where I said, this is 5, and what's this side? It's a 45, 45, 90. You can do this by either trigonometry or similar triangle. Okay, so what? Sine, cosine, or tangent? Sine. Sine or cosine, either way, because they're the same. Sine of 45 equals question mark over 5. Question mark is 5 sine 45. 5 root 2 over 2. Okay, so the top of this is at 5 root 2 over 2. Yay?
They could have just given it to us.
They could have, but
Yeah, but that'd be
they
so much.
expect you to demonstrate your education. So what's the distance? 5 root 2 over 2 minus y. The volume of the sheets. The volume is length, width, height. Now these are back to rectangular sheets. The length is
15.
15. The width, constant x or 2x? 2x. And the height? Y. An xy relationship. 5 root 2 over 2, run.
Oh, it's just one.
The slope is just 1. Yeah, it's south x and y are the same. Y is really the same. It's a 45, 45, 90. So if y equals x, then
X equals Y.
x equals y. So we can integrate 15 times 2y dy. Yes, sir. And use your calculator to evaluate. Okay. And don't forget the digits.
Plug in the stir.
Oh my goodness.
Answer?
792,792.20.
Okay. Do we agree?
I agree with Matt.
All right. That is the big idea of the day. So how do you calculate work? Row distance, volume, and integrate. Okay. Would you, so here's, first of all, we got 76, it's due today. Also, make sure your test corrections, you need to come in today, tomorrow, or at the very latest, Wednesday, they need to be done. 7th hour to get those done. I will be happy to give you help or help each other. 76 part B, I will put a key, actually I'll put answers and hints, not my work because that'll be copy fest, but answers and hints on my website. Look at it and be ready to finish tomorrow to class. Yeah, some of you are probably not rated polynomial division, so maybe I'll get an algebra 1. Did you know how to talk? Yes. Yes. Okay. Also, on Thursday, you'll have a second part of an AP test. It's not really something I expect you to prepare for, although if you want to prepare, I can review with you guys. Okay, there we go. On 76, you probably have a question on 10.
Yeah. Oh, yeah.
Okay.
That was just whack. Oh, yeah. Wait, no, I got it.
All right.
That's just sign
We'll see. So, are you ready? Okay, here's the deal. This is a little bit confusing. Yes. Okay. If I told you what's the derivative of sine, you would say cosine. But if I said, oh no, the angles are in degrees, now what's the derivative of sine? Not cosine anymore.
Oh,
Okay.
no.
So consider this. This is the idea. If I said graph sine in radians, and I said use a consistent equal scale, that big for one box in both x and y. Are you with me? All right. Now I could do that. 4, 5, 6, and so on. And I know that sine goes through the origin. It goes through pi over 2, which is about 1.571. It goes through pi 0, which would be right there. 3 pi over 2, about 4.5-ish. And 2 pi, oops, 4, 5, and like that, yeah? So here's sine. We? All right, cool, on a 1-to-1 scale. Now imagine then, if I took you back to set 27, when we said, all right, I want you to rough in or estimate the slopes. At 0, the slope looks like it's about 1. So at 0, the slope is 1. At pi over 2, the slope is 0. At pi, the slope is -1. Then the slope is 0. Then the slope is then slope is +1. And so we see that the derivative looks like cosine. Now, consider if instead we graphed in degrees, but on a 1-to-1 scale. So I'm not saying put 90 here. I'm saying on a 1-to-1 scale. So here's 1 degree, 2 degrees, 3 degrees, here's 1. So it goes through the origin, but where's that max point? Sine maxes out at 90 degrees, okay? So to get to that max at 1, I would have to go over to Mrs. LeBlanc's. You with me? And therefore, if I then connected that point at 1 Mrs. LeBlanc's room, the line would look like the curve, the sinusoid wave would be so flat, it would take forever to eventually get out there. Yeah? Now I think you can see then that if I then tried to estimate what the derivative is at 0, now it's not 0, and it's most definitely not 1 anymore. It's super flat. Now the slope is more like 1/60th-ish. And you would see that at 90 degrees it would eventually be 0, but so this would still kind of have a wavy component to it, but it would be super squished. You with me? All right. Now then, the idea is if our degrees are totally different magnitude of numbers, they're way too big for that slope to be 1. Slope is not 1 now. And that's why the derivative rules that we have studied, it has to be radian. It has to be. It does not hold true that the sine derivative is cosine if it's in degrees. Only if radians. Now, that said, if I want to figure out, does that mean I can't do it because it's in degrees? No, I must convert x degrees to radians so that I can use my derivative rule. What is x degrees converted to radians? What's the conversion rate from degrees to radians? Okay, 360 degrees, I put those on bottom to cancel out degrees, to 2 pi. Or maybe pi x over 180 if I took out a 2, yeah? So now I'm ready. I convert it to radians. I want the derivative of sine of pi x over 180 radians. What's the derivative? Times pi over 180. So at 0 degrees, what's the slope of the original problem? at 0 degrees, what was the slope?
Oh, pi over 180.
Basically 1 times pi over 180, 1/60th or so. Slope is very flat. Down? All right. So the point of that is all those derivative rules are totally dependent on the problem being in radians. All calculus is done in radians, never degrees. Understood? Dude, Lily, you're killing me.
Stop overachieving.
No, it's because I
Wanting
couldn't
to
like.
learn from your mistakes. Make me sick. All right. All right. Other questions on 76? 22, which is box 1.
Number 16.
18, 16, 20,
Just cross that out.
24. Okay, 22. All right, good stuff. This is cool. So you've got this circle x squared plus y squared equals any radius, which would be a full circle. But they said just take the top half. Okay. So like this, yeah? And then they say, all right, now I want you to take the calculus idea of volumes of revolution and develop the volume of a
Sphere.
sphere. Basically, we're doing this bad boy, taking this circle and making a volume out of it. Use a calculus. So if I take all these slices and revolve them, I get many cylinders, right? That is the concept. The calculus idea is summing many slices to make a complete three-dimensional figure. Pi is fine. The radius. Here's the radius, here's the radius, here's the radius, here's the radius. It seems like the radius is the curve. Okay? So if, in place of the curve, I put in r squared minus x squared, and what's the height of each slice? And by height, I mean thickness of each slice. And the height is dy or dx? It's dx. That way. So dx, and the limits of integration, 0 to r or negative r to r?
Negative r to r.
I'm going left to right, so it's negative r to r. All right. Now, thankfully, the integrand works out nicely because the square and the square root cancel each other out. A source of possible error is the variables. Are you integrating with respect to x or r? X. So when you integrate r squared, isn't it like integrating a constant with respect to x? So what's the antiderivative of r squared with respect to r squared x? And the antiderivative of x squared, negative x squared?
1/3 x cubed.
1/3 x cubed from negative r to r. You with me?
Yeah.
Okay, so when I go, r goes in, I get r squared times r or r cubed minus 1/3 r cubed. And when negative r goes in, I get r squared times negative r, which is negative r cubed, plus 1/3 r cubed. You down? What is r cubed minus 1/3 r cubed? 2/3 r cubed minus, and what's negative r cubed plus 1/3 r cubed? Negative 1 plus 1/3 is negative 2/3 r cubed. And what is 2/3 r cubed minus negative 2/3 r cubed? 4/3 r cubed times pi. The volume is 4/3.
Oh, sweet.
Yes, indeed. Awesome. All right. 18. 18 is integrating x e to the 2x plus x e to the x squared.
Good morning, Devlin Jaguars. Please rise for the Pledge of Allegiance. Please begin. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
How should we deal with the two different parts
All
problem?
students, tickets for the musical are now on sale. Tickets are only $5 at lunch or at the door. Visit devlinmusical.carousel.biz for
Okay.
more details. The show opens
So
next
integral, the
Friday,
first
January
integral,
31st
what's the
at 7
approach?
p.m. Remaining performances are
You
starting January
said
1st at 1 p.m. and 7 p.m.
ultraviolet
and Thursday,
radiation.
Saturday, February 6th through 8th. Students who want to take advantage of the drop-in peer tutoring opportunity, it will be available on the library
Okay, most stuff goes fine up to the
Sign up for the
dv.
teacher in any class you might need
What's the
extra help.
integral or the integral of e to 2x? Is it
Or miss those.
1/2 e to 2x?
Senior high students, attention all high school students potentially interested in
Okay,
taking
so
AP Chem, AP Bio, or
uv
AP Physics next year. There's an important informational
minus
meeting in the auditorium during
vdu.
7th hour today. Sign up with your current science teacher today for 7th hour or report directly to the auditorium. See you there.
Okay,
Thanks to
So-
all of your generous support during Wish Week last week.
what's
We
the
raised over
integrative now of that?
$13,000 for Rainbow in Colorado. Congratulations, Dad.
So let's leave the half out of it.
For your daily
What's the
day of the
integrative
day.
of e to
Happy
2x?
National Chocolate Cake Day.
Another 1/2.
That's all your announcements. Have a great day, Jag.
And leave off the plus c, we'll put it on the last one. You with me? Okay, what's the approach on the other one? U sub u is x squared, u is 2x dx. We do not have the 2, so bring it over. It becomes an integral of e to the u du, and what about the 2? 1/2 e to the u du. So 1/2 e to the u, might as well sub back at the same time, 1/2 e to the So two separate approaches. You down? Okay. 16, is 16 still a question? Another critical numbers, x natural log of x squared.
Oh wait, no, I'm sure.
We're done on 16?
Yeah.
20. 20 is hard to get started, or let's get the plan down. So it's got these two funky curve equations, neither of which I know what the graph looks like. It says show the tangents to the two curves at the origin are perpendicular. So what will we need to do to show the two curves, whatever they look like at the origin, to show they're perpendicular? What do we do? We'll need the derivative of each. So we'll need to find dy dx, that'll be implicit. And then we want to show that they're perpendicular, not any old place, but at the origin, okay? So find each at the origin. Will that then be a function anymore, or will that now be a number? That'll actually be a number, and then how will I conclude, or what will show that they're perpendicular? What do we know about perpendicular slopes? Negative reciprocals. They should be negative reciprocals. Okay, so that's the plan. Does that get you started? Now you can execute the plan, or do you want to walk through the calculus and derivatives? Or do you want to go on to 24? Okay, so you know the plan now. Execute the plan. And number 24. Find the exact area bounded beneath y equals 1 to the x on the x interval. So, So, if I, should be logs, yeah?
Yeah.
So you should be doing something like this. Log of x from 2 to 4. What should be log of 2? Okay. Well, yes, have a nice day. Bailey, can I give this back to you tomorrow? I'll try to make a copy.
Yeah, the answers are all, like, the questions are on the website as well.
Oh, the questions are posted, okay.
The questions and the answers are on the website, not the solutions yet.
What?
A mullet
That's my
mullet
face.
mohawk. That's so tight.
Put it in
Will they
the-
show you my work?
I don't think I they ever sent. Thank you, have a good day. I don't think I ever saw anybody before.
Okay, cause I kind of broke down.
Do they grade your work or do they?
Yeah, they grade your work on the final now.
You made a great
Yeah.
public grad students.
Unless it was Friday.
All
I
right.
answered a number of years. I was like, there's no way anyone would do that without a passed away.
Also, I think I just did not pick up the set
So
from
you did
Friday.
answer it.
Look out. It should be in that blue folder in the bottom basket. Probably, you see it on the bottom right basket, bottom shelf of the cart. A basket in the blue folder. Turn into the blue folder. No, it's in the basket. Sorry, the folder's in the basket.
Oh, there's a folder in the
Yeah.
basket.
And then you should be able to find. It's called 72B.
Wait, is that 76?
Oh, 76C. Excuse me.
Yeah.
Yay. All right. Oh man, this is not good. Okay, so this is kind of nice. Okay. What did they need? Oh, was it? Thank you. Have a nice day.